Good evening. I'd like to welcome you to this edition of the Della Pietra Lecture Series. We're very pleased today to have Jeff Weeks as our lecturer. Jeff received his undergraduate degree from Dartmouth and his PhD from Princeton University. He has taught at Stockton State College, Ithaca College, Middlebury College, and has spent much of his time as a freelance mathematician. Jeff is extremely well known for using computers to help visualize geometric problems, especially in dimension 3, and in a very related area endeavor to use these programs and geometric computer visualization to help teach students about geometry and symmetry, and I think we'll be seeing some of that this evening. Jeff, among his other honors, received a MacArthur Award. I've got that right, don't I? The Genius Award for his work in low-dimensional topology. And to me, he's very famous because he has a manifold named after him. And I could think of only one other living mathematician with a manifold named after them, and many dead ones like Poincaré, Hilbert. Does Gauss have a manifold named after him? No, he only has curvature named after him. So Banach. And we're very pleased today to have Jeff. The title of his talk is The Shape of Space, and I think we'll learn how to visualize three-dimensional spaces.
Hey, thank you. So I'd like to start by thanking the Della Pietra family for sponsoring the lecture series, and thank the Simon Center for hosting it here. It's a real pleasure to be here. This evening's topic is space, and you're looking here at a picture of deep space that was taken by the Hubble Space Telescope. And there's actually a pretty interesting story behind this picture, because normally it's very difficult for researchers to get observing time on the Space Telescope. Literally every minute is precious. But the director of the project, as one of the perks of his job, was given a full 2 weeks to look at whatever he wanted. And so naturally people were curious what he was going to look at. Maybe star formation, black holes, maybe study the evolution of galaxies. But do you know what he decided to look at? Nothing. Okay? He picked a little tiny patch of black sky up near the handle of the Big Dipper where nobody had ever seen anything. And he pointed the Space Telescope at that little patch of sky. Well, with a regular camera, you might take an exposure of, say, 1/60th of a second. So he pointed the Space Telescope at that little patch of sky and took a 10-day exposure on it, and this is what he saw. So as you can see, the universe contains galaxies of various shapes and colors. Okay, a typical galaxy contains about 100 billion stars. Okay, not 100 million, but 100 billion. So, okay, it's less than the federal budget deficit, but it's still a lot. Now, in this picture, you can see a few hundred galaxies, but remember that it covers a tiny part of the sky about the width of a dime as viewed from 75 feet away. So you folks up in the back there, I think you're probably getting the right perspective on this. Now, if we were to look this closely at the whole sky, we'd see, coincidentally, about 100 billion galaxies out there. So we're looking out and we're seeing 100 billion galaxies, each with roughly 100 billion stars. So for sure, the universe is very, very big. But the question is the universe truly infinite? Or might there be some limit to the volume of space, some limit to the number of galaxies? In other words, might the universe be finite? Now, there's an old argument due to the Greek philosopher Archytas that says, well, if the universe were finite, then we ought to be able to walk to the edge. Okay, and we got to the edge, well, we ought to be able to stick our hand through and find something on the other side. Now, Architas interpreted that argument to mean that the universe must be infinite. But if you think about it, what it's really telling you is you don't expect the universe to have a boundary. Okay? And being infinite and not having a boundary are two different things, it turns out. In fact, there are many ways to have a finite universe that has no boundary. So that's what we'll be looking at this evening. The plan here is to first look at some toy two-dimensional universes, and once everybody's happy with the main ideas in 2 dimensions, then we'll come back and look at the real 3-dimensional universe again. Okay, so let's switch to our toy 2-dimensional universe. Here it is. We have a flounder living in it. Clearly, it's finite. Okay, and at first glance, it looks like it has a boundary. Okay, but really it doesn't. When the flounder swims off to the right, she comes back from the left. When she swims off the top, she comes back from the bottom. So this kind of universe is called, let's find it here, a torus. Okay, so how can you understand a torus? Well, if this is your torus, side to side, the torus wraps around like a cylinder. So the flounder can swim off to the east and come back from the west. But a torus, unlike a cylinder, a torus is also like a cylinder going top to bottom. So the flounder can swim off to the north and come back from the south. Now, if you take a piece of paper and you try to glue the top to the bottom and at the same time glue the left side to the right side, you just get a crumpled mess. It doesn't work very well, so we're going to stick with the software. Okay? Okay, it's a toy universe. What do you do with toys? You play games. So let's play some games on this torus. Okay. We can play one of the other ones in a minute here if you want. I'd like to warm up with Tic Tac Toe. So I propose we start with all of us against the computer. Where shall we go for our first move? Young man in the front left there.
Top left square.
Okay, everybody happy with top left? Yes? No? Okay, we'll go with the top left. And there's the computer move. Okay, now where should we go? Yeah.
Up in the middle.
Up in the middle. Okay. If you hadn't wanted to go in the middle, maybe if you want to go in the side instead, we could, this torus, it's like a cylinder. Okay, and you can take a cylinder, one moment guys, you can take a cylinder and roll it around. So we can take our torus and roll it around as well. But remember, it's also like a cylinder top to bottom. We can roll it around this way. So if you didn't like that top middle, we could roll it around. Okay, we could even stop a little sooner if you'd rather see it there. Yeah, suggestion here.
The one under the X.
The one under the X. This square here. Should we go here? Oh. So I guess. Okay. Now, what I would like to propose here is a game. We'll turn off the computer's role in this. I would like to propose a game of the kids versus the adults. Okay. So could I please have one representative from each group? Okay, young man here. Come on up. And you don't actually need to decide the move. You just get to decide, get your team's consensus and mark it down. And we'll get a grown-up representative here in a moment. So here, come on around here. It's human versus human. Let me clear the board. Okay. Okay. Can you see it, or would you like a boost? You can see it. Great. Okay. So the way it works is you can click the hand within a square when you're ready to make your move, or if you grab one of the grid lines, you can scroll it around. Okay, so want to get your team's opinion for where to move and click it in?
You guys.
Okay, you can come up here. Show it.
Whatever you want here.
The brain trust.
what do you think, guys? But where to move? I see.
No, the riddle.
Are you kids okay with that spot? Would it have, some of you wanted it there? Some of you wanted it there? Okay. Okay, one moment now. We need a representative of the adults. Anybody willing to be thrown to the lion? You're not an adult. Anybody willing to be thrown to the lions here? Okay. Gentleman in the red.
Can I move the board?
You may. So you can either, if you grab a grid line or an already marked square, there's a mouse if it's easier. Okay. So we now have okay, kids. What'll it be?
I guess I.
It's now or never.
Okay. Adults move. Not a lot of choice for the adults here. Okay. Got to make it hard for them.
You better give the computer an error.
Okay, actually we should. Actually, that's the O's for the adults. Maybe we should put that there. Okay.
Seriously.
Oh, we don't want to make them sweat more than that? There we go.
Hey, I didn't try it.
Okay, I think we need to, yeah, there you go. Okay, so what do you think, kids? Where do you want to be moving? Okay, your team has some ideas here. Better.
You, me? Yes. Okay.
Don't listen to me.
On the bottom, in the middle. Like, no.
Okay.
Yeah.
Okay, well, we can scroll the board around if that makes a difference to you.
My dad's gonna win. Right there. No, now there.
Okay, good. Thank you. Okay, a round of applause for volunteers. Thank you. Thank you. Okay, while we're here, would you like to try one of the other games? Chess? Okay, chess is a little long. We can start a chess game, and then I'll tell you what, you can download this at home for Mac or Windows or iPad. If you go to www.geometrygames.org, and then you can play at your leisure. It's free, don't worry. Okay, oops, let me turn it back on to human versus computer here. Okay, so we're playing the white pieces, the computer's playing the black pieces, and the chess pieces move exactly like in regular chess, with the exception of the pawn, which in the interest of symmetry, if the pawn is not capturing, it moves one space up, down, left, or right. If it is capturing, it moves one space along any diagonal. So where would you like to go first? Okay, who hasn't answered yet? Well,
2 times.
anybody else? You've answered. Anybody else have an idea for where we should go first? Even adults can shout out something if they want. Okay, no response from the adults. Okay, oh, there's somebody back there. Okay.
Knight up.
Okay, if we move the knight up, so we can go 1, 2 up, and left or right?
You have to make it out with it.
Left.
And left. Okay.
Oh, congratulations.
So we've checked the king. But didn't finish so well there. Now what?
Peter.
Down here. Well,
Sorry.
any other ideas?
The pawn up.
The pawn up. Something funny happened there. Well, anyhow, so you see how this goes. We don't really have time to play a full game now. We could take it, but then we lose our queen. So So you're welcome to try this at home. Now, though, I'd like to ask you a question. And the question here, let's zoom out. And my question for you is, if this flounder looks straight ahead in this torus, what does she see?
Tail.
Yeah, she sees her tail. Her line of sight wraps all the way around. She sees her own tail. So she has the illusion, she looks forward, she has the illusion of seeing another flounder sitting out here somewhere. How about if she looks to the north? What does she see? Yeah, her line of sight wraps around. She sees her own tail. She has the illusion of seeing another flounder up here. How about if we move that shell out of the way and she looks to the northeast? What does she see?
No, she see the crab.
Yeah, maybe the crab. Let's see. So her line of sight wraps top to bottom, side to side. She does indeed see the crab, so we'll get it out of the way. And she sees her tail. So looking to the northeast, whatever, she has the illusion of seeing another flounder sitting up here. So in effect, she has the illusion of living in an infinite universe. Okay? So even though, for example, there's really only one crab, the flounder sees it in infinitely many directions. Okay. Okay. So let's zoom back in here. So what do we got here? We've got a nice universe. It's finite. It has no boundary. The only slight problem is that this is a two-dimensional universe, and what we'd really like is to have a finite three-dimensional universe without a boundary. So my question for you is, how can we make a finite three-dimensional universe for three-dimensional people like us? Let's see. Anybody else? Let's see. Got an idea? You? Yeah.
That can make a strip, like a cube.
Yeah, we could start with a cube. Okay. In fact, we could start with any rectangular block of space. It's like the space inside this room. Ignore the fact that the floor slopes upward, please. Okay, so here we are inside this roughly rectangular block of space. When I walk out this way, I'm not going to crash into the wall, but what's going to happen? Yeah, I'm going to come in over there. And if I walk through this front wall, I'm not going to crash into the blackboard, but what's going to happen? I'm going to come in the back, exactly. And how about if I fly up through the ceiling? I'm going to come up through the floor. Great. This sort of universe is called, it's called it's called a 3 torus, just like the Flounder's world was called a 2 torus. Okay, so we're in our nice 3 torus here. When you look straight forward, what do you see? Yeah, us. Okay? Because your line of sight goes out the front wall, comes in the back wall, hits the back of your head. So we're looking forward. We have the illusion of seeing another room full of people that, amazingly enough, they all look just like us. Okay. How about if you look to the right? What do you see? Us, yeah, because your line of sight goes out the right wall, comes in the left wall. So we're looking off to the right. We're having the illusion of seeing another room full of people, and they look just like us, too. How about if you look down beneath your feet? What do you see?
Our heads.
Yeah, you see your heads because your line of sight goes down through the floor, comes in through the ceiling. You see the tops of our heads. They can see the tops of our heads really well. Let us have... Actually, before we see this, did you want to ask a question? The guy in the middle there. Yeah.
Can you use that with mirrors?
Can you use that with mirrors? This is very similar to the effect when you have mirrors on opposite walls. You see lots of repeating images. The only difference is, if we stand here, we see another image of ourselves over there. As we walk forward, is that other image, is it walking towards us or away from us?
Towards us.
Let's see. Let's try it with the flounder here. Okay, so the flounder, here she is. She has the illusion of seeing a copy of herself. As she swims forward, is that other copy swimming towards her or away from her?
Away.
Yeah, it's swimming away. If she swims to the north, it swims to the north. When you look at a mirror and you walk towards the mirror, does your image in the mirror walk towards you or away from you? towards you. So that's the difference. It's almost like the mirrors, but here the images go in the same direction where the mirror goes in the opposite direction. Yeah.
So are you basically talking about a reflection?
No. It's similar to a reflection. You see another image. It's very much like a reflection in that you see something that looks like another person who looks just like you. But you know that it's not really another person. It's just another image of you. So in that sense, it's very, very much like a reflection. But the only difference is that in the mirror, you walk towards the reflection, and it comes towards you. In this 3 torus, the flounder walks along, and her image never moves towards her. It always goes the same way. So it's kind of like a reflection. It's a lot like a reflection, but it's kind of different, too. Okay? Okay. Let's use the computer to illustrate this effect in 3 dimensions. Okay. Here we're in a 3 torus containing a single Earth. Okay, let's start flying. Whoops. Oh, I didn't mean to crash into it. Oh, I see my mouse. Let's restart this. I'm going to lose my 3 torus driver's license here. Okay. Okay, so we'll avoid the Earth. And when we pass through that wall, you know what's going to happen? We come in from the opposite wall. There we are. And we can cut little windows so we can see where we're going. So our line of sight wraps all the way around this finite universe. And so we have the illusion of living in infinite space.
You gotta be kidding me.
Okay, so there we are. Okay, so that's one possible shape for space. Now I'd like to look at some other possible shapes for space. What do we want? Let's zoom back out here. In 2 dimensions, another possible shape instead of a torus is a Klein bottle. Okay, what the heck is a Klein bottle? Well, side to side, a Klein bottle is just like a torus. Okay? But top to bottom, it's glued with a flip. So anything that goes out in the upper right comes in on the lower left, and vice versa. Now, of our flounder, if she swims straight up the center, she's going to come back in the center. But what's different about her? Notice anything different? Here she is before, and here she is after. Yeah, she's upside down, or if I make her right side up, somehow this kind of gets back to your question about being like a mirror. She comes back as her mirror image. Yeah, okay. Yeah, she comes back reflected. She comes back as her mirror image here. Okay, want to try one of the games in a Klein bottle? Maze? Okay. Okay, let's try a maze here. So each maze is different, so I don't know how to do this. You'll have to call it out to me. Okay, which way do I want to go from here? Left. Okay, down. Up, up. Left. Now keep going or go up? Up, up. No. Left. Okay, keep going. Oh, there we go. Oh, that wasn't so bad. Okay, that was pretty quick. Want to try one of the other games? Crossword? Okay. Crossword here. Okay, let's do maybe the second one, I think, here. Okay, a crucial point here. You see that little yellow arrow? There's a reason for that. Okay, do they justify the means? Anybody know what that might be a clue for? Yeah. Ends, very good. Okay, so there's ends, and you'll say, well, why the heck do we have the little yellow arrow? Well, you know what's going to happen when we push that up?
It's coming up above.
Yeah, remember what happened to the flounder? She got flipped around, came back as her mirror image. So when this comes back from the bottom, it's now reading right to left. So that's what that little arrow is for, to tell you whether you should expect the word to go left to right or right to left. Okay, let's try some of this. Primary or principal, 4 letters.
Main.
Main, yeah. Main. And let's see, what else do we have here? This is going right to left, but, well, we could fix it. Oh, let's go right to left. Departed. Oh, that's a tricky one. But left, let's see. Well, right, left, but we'll see how it works out. There are a number of possibilities there. Want to try some of the vertical words here. Courier. Messenger, M-E-S-S-E-N-G-E-R. Well, that fits. How about here? We have a common yellow flower with lots of letters in it. In fact, this is the right season for this common yellow flower. I think we have more letters. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 letters to deal with here. Well, we can come back to that. Dandelion. Good. Yeah. How about D-A-N-D-E-L-I-O-N? Okay. So how about for departed? Instead of being right to left, we can make it be a left to right word. Gone. Okay for departed. Yeah. And what a couple things are missing here. We have left to right, fuse two pieces of metal. Weld. And last but not least, by any other name would smell as sweet. Rose. Okay, very good. Oh, we got the vertical word for free. Okay, a question for you now. If we go back to our flounder, and let's get rid of the axes, and let's zoom out. Now, my question for you is, if this flounder looks due south here, does she see the pink shell or the red shell?
Pink.
Pink, red? Hard to say. We're in a Klein bottle here. Yeah, we're still in the Klein bottle. So because of this flip, she sees the red shell instead of the pink shell. So she, like in the Taurus, she has the illusion of living in an infinite universe. But this time, the pattern of the images is different. Okay? So an observant flounder could tell not only that her universe is finite, but she could also tell whether she's living in a Taurus or in a Klein bottle. Okay? Okay, let's go back to 3 dimensions. Yeah, me too. Okay. So here we are originally in a good old 3 torus. And here we can take, whoops, that's not the key I wanted. Hang on. We can take this Earth and move it around, so we can move it out one wall, back from the other, push it up this way. Okay. Now, if we switch to Klein space, now we can take the Earth side to side. It's just like the torus, no different. But top to bottom, it's glued with a flip. So what's going to happen to that Earth if I take it and push it up through the ceiling? Yeah, somebody says it's going to do this. It's going to come back as its mirror image. Let's do it. There we go. Let's move it closer here. Notice anything funny here? So there we have Africa, then we have the Atlantic, South America, North America,
Awesome.
then the Pacific. On the eastern Pacific, there's Australia. We're back to Asia again. Pretty soon here, we'll be back to the US. Okay. Long Island's on the west coast now. Okay. How about if we take this Earth and push it up through the ceiling again, what's going to happen?
Back to normal. Back to normal.
Back to normal. Very good. There we go. It flips again and comes back to normal. Okay, I'd like to show you one other space that has no analog in 2 dimensions. Okay, so in this space, side to side, just like a torus. Top to bottom, just like a torus, no flip. What's different here is we're going to take the back wall and glue it to the front wall with a 90-degree rotation. Okay. So now if we take the Earth and push it out through that front wall, it comes in the back wall rotated. Can we go through this? You bet. Okay, let's do it. Okay, the question was, can we go through this? Okay, so we're going to fly through that front wall. Let me pause for a second. So what's going to happen when we fly through the front wall? Yeah, we're going to go out the front wall, and then we're going to come in the back wall, rotated 90 degrees. Okay, let's do that. Why? That's just the way we connected it up. So we're rotated 90 degrees. So there's our, once we're rotated, the floor is to our side. So that's the original floor on the right, the original ceiling on the left. How about if we go through that wall again? Yeah.
Can you make holes again in the walls?
You bet. We'll do that. In fact, let's finish this trip. Then we'll do exactly that. OK, so here we are. We've rotated 180, so we're upside down. There's the original floor above us, the ceiling below us. If we go through again, yeah, 270. So here's the original floor to our left, the original ceiling to our right. How about if we go through again? Yeah. 360. You bet. And there we are, 360. We're back to where we started. Now, the suggestion from the young man in the red shirt there was, can we make holes in the walls? An excellent idea, so we can see where we're going. Okay, let's do that. Whoops, we're not very straight. Let me get lined up first. Okay, there we go. Now let's make holes in the walls. So we're still flying around this finite universe, but we get the illusion of infinite space. Yeah. So now the repeating images tell us, that's our clue, that the space is finite, that we see repeating images. And if we study it closely, then the pattern of the images tells us the shape of the space. The pattern of the images tells us whether it's a 3 torus or a Klein space, the space with a 90-degree turn, or maybe something else. Okay, great. So we have these different possibilities. So, well, what about the real universe? Let's, Klein Bottle, we've done that. What's last year? We've done that. Okay. So to test whether the real universe is finite, in principle, we ought to be able just to look out there, look around, see whether we see repeating images of our Milky Way galaxy. But it turns out that it's not as simple as it seems at first glance. So what's the problem? Why can't we just look out and either see repeating images of the Milky Way galaxy or not?
It'll be the Milky Way galaxy a long time ago.
Yeah, it'd be the Milky Way galaxy a long time ago. So are we seeing these other galaxies as they are today? No. Why not? Light travels a long distance, takes a long time to get here. Okay, so in particular, so if we're here, we're looking out into space, we see nearby galaxies as they were recently. We see more distant galaxies as they were further in the past, because it takes the light longer to reach us. We see really distant galaxies as they were just being born, as they were condensing from clouds of hydrogen gas. If we look even further, we see the primordial plasma from which that hydrogen condensed. Now, the plasma is opaque, so we can't see any further than that. But please do not feel too bad about this, because we're looking back 13.7 billion years. The beginning of time is only 380,000 years beyond that. So we're seeing 99.997% of the way back to the beginning of time. Now, this is true no matter which direction we look. We look at any direction into space, we're seeing back to that plasma. So our horizon is this huge sphere filling the whole sky with us at the center. Great. Does this mean then that we could go outside tonight, wait for a break in the clouds, look up into the sky, and see this plasma on our horizon? Well, yes and no. Okay? The plasma really is there. Okay? The catch is that the radiation we receive from it arrives not as visible light, but as microwaves. Now, if human eyes were sensitive to microwaves as well as to visible light, then the night sky might look something like this. So we could look out, we'd still see nearby galaxies as they were recently. We'd see more distant galaxies as they were further in the past. We'd see really distant galaxies just being born from clouds of hydrogen gas. And then behind it all, on our horizon, we'd see this plasma. Now, in the plasma, there are hotter spots and colder spots. Well, I should say, in the plasma, there are denser regions and less denser regions. Now, the radiation, the photons, the microwaves coming from more dense regions, to get to us, they have to do a little extra work against gravity, and they arrive a little bit cooler. The radiation coming from less dense regions, it does less work against gravity. It arrives a little bit warmer. So in effect, we're looking out and we're seeing density variations in the early universe. Now, you might be wondering, what does this have to do with whether the universe is finite or infinite? Well, we're getting to that part now. Okay. Here's a cartoon view of the primordial plasma superimposed on the modern galaxies that it evolved into. This red circle represents our horizon sphere. Now, in an infinite universe, the plasma has these density fluctuations, and in an infinite universe, those fluctuations can be as broad as you like. And in particular, you'd have broad density fluctuations on the horizon. In a Taurus universe, or in any small finite universe, the density pattern repeats, like the repeating images of the Flounder that you saw earlier. So in particular, the density fluctuations can't be any broader than from one image of a galaxy to the next image of that same galaxy. So in effect, in an infinite universe, you expect, broad density fluctuations on the horizon, while in a small finite universe, you don't. So if you want to test the real universe, you just need to look at the sky with a microwave antenna. Okay. In 2001, this Delta rocket launched a satellite called the Wilkinson Microwave Anisotropy Probe, which it's kind of a mouthful. That's the last time you'll hear me say it tonight. Most people just call it the MAP satellite. Now, the MAP satellite orbited the sun in synchronization with the Earth and observed the microwave sky for 9 years. And here's what it saw. So this is the horizon sphere for the real universe as seen by the MAP satellite. The cool thing about this picture is that it lacks the broad fluctuations you'd expect in an infinite universe, suggesting that the real universe could indeed be finite. Okay? More precisely, the broad fluctuations are weak at the 1 in 3,000 level, meaning that you could get such weak fluctuations even in an infinite universe just by chance, but only one time in 3,000. Okay? On the other hand, the fluctuations you see when you study them more closely, they don't really look exactly like what you'd expect in a 3 torus universe either. Okay? A better candidate is the Poincare dodecahedral space. Okay? Now, what is this? Well, we'll see. It's the dodecahedral space. It's like a 3 torus, but made from a dodecahedron instead of a cube. Okay? Let's go inside. Okay, so we're inside this dodecahedron. When we fly out across one face, you know what's going to happen? Yeah, we're going to come back in from the opposite face. Okay, let's cut some little windows so we can see better. Yeah, exactly. Okay, we can make the windows wider for a better view. And I'll just fly through the spiral arm here. Of course, in the real universe, Mother Nature doesn't show us these walls at all. So we'd see something more like this, and it would be up to us to figure out the shape on our own. So in effect, the Poincare dodecahedral space it's kind of like a 3 torus, but instead of having a universe based on a cube with images repeating along a cubical lattice, instead of that, we have a universe based on a dodecahedron with images repeating along a dodecahedral lattice. Now, the kicker here is that a dodecahedral lattice cannot exist in flat space. Okay? Instead, it exists on a hypersphere. So it's kind of like we're flying on the 3-dimensional surface of a 4-dimensional ball. So the real universe really does have the shape of a dodecahedral space. It means that space is not only finite, but also slightly curved. Okay, there we go, slightly curved. Okay, how curved would it have to be? Well, imagine for a moment a sphere. Okay, you can have smaller spheres, you can have larger spheres. A little tiny sphere like a ping pong ball curves very tightly. A bigger sphere like a basketball, it curves more gently. Okay? A sphere as big as the whole Earth curves so gently that it looks almost flat. Now, it turns out that for the dodecahedral space to explain the missing fluctuations, the dodecahedron has to fill about 80% of our horizon sphere, okay? Which corresponds to a curvature of a little under 0.02 on this scale. Now, with the original map data, along with a bunch of other experiments, it gave a measured curvature for the real universe of 0.02 plus or minus 0.02. So, looked pretty good. Then, in 2008, some newer data came along that pushed that estimate down a bit, suggesting that, well, maybe this dodecahedral hypothesis isn't so useful after all. Okay? Fortunately, in 2009, when researchers folded the Sloan Digital Sky Survey data into the mix, that pushed the curvature back up a bit, so the dodecahedral model is still consistent with observations. Okay, so in conclusion, the universe might be flat, or it might be slightly curved. It might be finite, or it might be infinite. The only thing we know absolutely for sure is that Mother Nature has more surprises in store for us. So thank you all for coming.
I think we have time for some questions.
Yes?
I was curious, it's more of a technological question. I mean, we're familiar with the idea of the 2 mirrors on opposite walls.
Yeah?
But could you imitate a torus, like with some video screens and cameras embedded between them, and give the illusion as you walk towards one wall, you're really walking away from yourself? It might be a little expensive to produce, but could you
Let's think.
that?
Yeah, I think this would be very cheap because you have this cave technology where you have a sensor that monitors where the user is and which direction he or she's pointing his or her head. And with that, well, once you have that, then even with the same software like this, you just tell it where you want the user and then project onto the walls what the user would see in each of those.
Just cameras on the walls projecting what is really there. So an actual room with.
Well, but what's there,
Video.
yeah, what would go on the wall would depend on the observer. That if you and I are both looking at that wall, and we both look at, say, the center point, I'd see what's back there while you'd see what's up there. Yeah. Other questions?
Is there a twist in this dodecahedron? So you go and you go 5th turn or something?
Yeah, the twist in it. Let me hide the galaxy for a moment here. View, side piece, none. Okay, with a cube, you can glue faces straight across. With a dodecahedron, you can't glue faces straight across because opposite faces are offset by 1/10 of a twist. So if you tried to go straight across, the corners of one face would be lining up with the middle of the edges of the next one. So you're forced to twist it a little bit one way or the other. In this case, all the faces have a consistent 1/10 of a twist. They're either all clockwise or counterclockwise, and I don't remember what it is, but you can figure it out here. Well, if I turn on, I wanted a gyroscope. If you look at this little gyroscope here, then you can see as you march along, well, maybe it's not so visually clear. You can kind of see that the gyroscopes rotate around 1/10 of a turn each time because of that 1/10 of a twist. Let's see.
Yeah, since the universe is expanding, is there any way to explain that using this model?
Oh, in fact, with finite universes, I think it's even easier to understand the expansion of the universe than an infinite universe. So say we're in our 3 torus universe made out of this room here. Okay, as the universe expands, the way to understand this is not that it's expanding into anything or that, but it's like between every pair of seats, you're staying the same size. Every person, you're all staying the same size. Your seats are staying the same size, but the space between seats is getting bigger. Maybe at some rate of 10 centimeters per minute. That space is stretching out. That applies to every pair of seats. And furthermore, it applies to the distance between this seat and its counterpart over on the left. So I can just reach my hand over that other seat. I'm touching it right now. So that distance is also increasing at, say, 10% per minute. So the whole universe is just gradually getting bigger. That's the same picture that you have in mind for an infinite universe, but just somehow the human mind is more comfortable with a finite universe because you can kind of see the volume getting bigger, whereas with an infinite universe, well, the volume was infinite to start with. It's infinite afterwards, but even still, it's expanding. Did that address your question?
Yes.
Okay. Young man in red.
Well, if you had like a hologram of a sphere, but then when you looked at it, and you turned around, it would look different to represent like a hypersphere.
Yeah.
So if you look at it one way, you would see something, but then if you go over here and look at it, you would see another thing, but it's still part of the same hypersphere. Would that help to understand that? Because of the curvature?
Yeah, so you're saying eventually having some sort of hologram that shows you the right thing from each direction? Yeah. Yeah, that sounds good. Young man in blue.
Could it be possible to use a sphere and like if you stretch it and like if it's expanding and you're stretching it, could you like make it? Can you see infinite universe if you have holes in it?
Okay, I think if you have a sphere and it's expanding, are you imagining like a sphere, like a hypersphere that we're living on the surface? Are you imagining being inside a sphere?
Like inside the sphere. Like the universe is like a sphere.
Oh, inside a sphere. I think that's, people are hesitant to work with those, and the problem there is that inside you're okay, but then you have the edge of the sphere, and you get back to that problem that worried Archytas 2,500 years ago, that if you had an edge to your sphere and you went to that edge and you stuck your hand through, what would happen? And I think that troubles many people, myself included. Okay, other questions? Yeah.
There's 2 types of curvature, right? Positive and negative. And you've shown one. You didn't say which one it is, but do you have an example of the other?
Sure. Okay, this is positive curvature. And in fact, the giveaway telltale sign here that it's positive curvature is if you look way back in there, you can see that there's some more distant objects that look bigger than nearby objects. And the reason they look like that is imagine, so we're going to bump down a dimension. And by the way, I should put in a plug for my favorite book here. If any of you kids or adults either, if you've never read Flatland, you should get a hold of this. It's a beautiful book. It tells you about how a 2-dimensional creature comes to understand a 3-dimensional world and then helps 3-dimensional creatures like ourselves understand a 4-dimensional world. But one lesson from that book is that it's always, whenever you don't understand something in one dimension, it's often very useful to think of the same question in a lower dimension, then come back to your original question. So you were mentioning about the positive and negative curvature and saying, well, why does that thing look so big? Well, if we're confused in a three-dimensional space, let's go to a two-dimensional space. Imagine the surface of a sphere. Imagine we're up at the North Pole, and our line of sight goes out like so, but then our line of sight, it converges back in towards the South Pole. So even if we had a very small object near the South Pole, it would fill a large part of our field of view. So that's what's happening there, that gyroscope looks really big. If we're at the North Pole, it's near the South Pole. So that's the clue that we're in a spherical space here. And the question is, well, what about the opposite? In 2 dimensions, spherical geometry is one possibility. You have flat geometry, like the floor or the walls. Then you can have spherical geometry, like a basketball. And the other possibility is hyperbolic geometry, which is like the shape of a saddle, is one way to think of it in 2 dimensions. But the request was for a 3-dimensional space. This one will do. OK. So here we're in a hyperbolic space. And let me turn off the fog so you can see a little further. And now it's the opposite effect, that in the spherical space, distant things look bigger than you expect. Here, distant things look very small very quickly because they're filling less of your field of view. Hey, all right. OK. What do we have? Take another question or two? So, yes.
Professor, a little bit question about the picture that when a person observes the universe, the origin of the universe comes like in a circle of. I just wonder why, and does it have any correlation with the Riemann sphere?
Could you repeat the question, please?
Yeah. Well, you give a picture in the slides that when a person with a telescope observing the universe,
yes.
The origin of time and space, the origin of the universe, which is the green part, it surrounds the whole.
Yes, so you're looking back to the beginning of time and seeing the horizon.
Why the beginning of time that's surrounding everyone? I mean, if you look, do you mean that if no matter which direction you look at, then you will see the origin of the.
So we're looking back. I think I understand the question. And tell me if this answer is what you're looking for. So when we look out into space, we see all the way back to the beginning of time in all directions. But you're saying, well, are we also seeing the point where space began? And the point where space began is a tricky concept. Because imagine, we were talking earlier when somebody asked about the expanding universe, and we said, okay, well, imagine we're in this room here, and the seats are all moving away from each other. Take that mental picture and run the movie backwards. So now the seats are all getting closer. So you're not getting any smaller, but the distance between you and your neighbor is getting smaller. So you're kind of getting squished in as the space gets smaller in all directions, and it's getting more and more cramped, and then we're all kind of pushed together in one blob, and then it's a gruesome picture running it backwards, but our bodies just get smashed in, and eventually the atoms that make up our bodies get smashed in, and we all turn into this super dense plasma, and we go back, and then we're like neutron stars or something. We get denser and denser and denser as this 3 torus. Everybody seen this 3 torus universe collapsing down to like the size of a sugar cube with all of us in it, and then smaller still. When it gets down to 0 size, that's the Big Bang. Okay, so when we talk about seeing back to the beginning of time, we're seeing back actually not quite to the Big Bang, because we can only see to the point where, running the movie forwards from that super dense thing, we get the plasma, and eventually it gets big enough that the plasma condenses to a gas. The plasma is opaque. The gas is transparent. So then light can travel. So we can't see past that plasma stage. But what point we're seeing, well, it's not the same point in all directions. Okay, because the universe had some small finite size when we saw the plasma. But even if you could see back to the beginning of time, I think the exciting thing to me at least, is the idea that the universe didn't begin in one particular place, but the Big Bang was the whole universe being small and then expanding. Does that address your question?
it can help me understand if I take the expanding universe model into consideration. And a little bit suggestion about your example with the Flounder to illustrate the Taurus and the Klein Bottle. For Taurus, it's totally fine, but for Klein Bottle, since they are like flat, but the fish, the Flounder, which is right eyes is on the right side of the body.
Yeah.
The left side. It's no longer a Flounder. It's a fluke, which can sell higher price.
Oh, I know. Let's see. In fact, in English, we don't make this distinction. Are you Japanese?
I've got a lot of friends who like Japanese, and I know that for Flounder you can just broil or stew, but for fluke you can make sashimi with that, which is just kidding. Sorry.
Yeah.
Just kidding.
Because in English we don't make a big distinction. In Japanese, there are two words for the left-handed and the right-handed ones, and in fact, the guy who wrote the Japanese version, in the explanation, he used this very extensively to refer to left and right-handed. Shall we break up and take questions here up top?
Thank you all very much for coming. And
thank you. Okay. Yeah, if you have more questions, just come on up.